Welcome back to the Outpost. Today we're going to talk about grid magnetic angles and how they relate to land navigation. This is the technical math part of land navigation everybody hates. Once you get the basic principles down and a few of the formulas, it's pretty easy to do, but it's math and math sucks for some people. So let's see if we can learn something. All right, we're going to talk about what declination is, and that's basically the grid magnetic angle. Grid would be your map. Magnetic would be your compass, but it's the angle that where north would be as those two relate to each other. Remember, we've got a flat map that we on a round Earth, and then we've got the North Pole up there at the top. And because those representations aren't equal, there's going to be some errors in the math. The grid magnetic angle is going to correct those errors. We've got a couple kinds of north. We've got true north. That's where the north's actually at, the least useful one to our navigational purposes. We've got our grid north. It's usually the center of the map, and that's where the map says north is. And then we've got our magnetic north, and that's where our compass says north is at. These things can change over time. There's a internet link right there to NOAA, and I'll put that in the description, but that's where you can update or check to see if the angle is still accurate. My map key here, we can see a depiction of the declination. You can see that stars where true north's at, and we've got our MN, which is where our magnetic north's at. Our grid north, our GN, pretty much is going to be the same as our true north. And then there'll be, this one said 18.5 degrees as the correction. Why do we care? Why does all this math matter to us? If you're just doing terrain association, you've got major features on your map and there's not a lot of tree cover, and you just need a general idea where north is, you probably don't care at all. If you're going to do precise navigation, you need to know this, because a few degrees difference will mean a large difference over a large terrain movement. So if you're going to go a long ways, you're a few degrees off, you're going to be way off trying to find a specific place. If you've got a lot of tree cover, it's going to be harder to navigate because you're not going to be able to see major features because your visibility is limited. Jungles, the heavy boreal forest like we've got here in the Pacific Northwest, great examples of that. Or if you've got flat, featureless terrain. If I'm trying to find a very specific location in a desert that's super flat, the ocean, anything like that, we need to be as precise as possible, because if we're a few degrees off, then we're never going to find the place we want. The reason we care is we don't want to get lost. Okay, we've got a couple formulas here. If you've got an east declination, so I live and have pretty much always been in part of the United States where it's been east declination, west coast. So it's going to the right side of true north. So if we remember, we've got north, south, east, and west. If it's going that way, it's going towards the east. If it's going this way, it's going towards the west. Where does that lie? That line pretty much follows the Mississippi River down if you want a big major landmark. So if you're going to be near that, you're going to be close to zero, and this math won't be quite as important to you. But these are the formulas you'd want to write down. Where I'm at, you've got your grid angle minus your declination becomes your magnetic angle. Or if I've got a magnetic angle, I add declination to become a grid angle. The way we remembered it was, if you're a general, G, and you want to get to a major, M, you're going to go down because they're less in rank. And vice versa, if you're a major and you want to get to a general, you're going to go up in rank. That only works on the West Coast, and it only works if you know the difference between a general and a major. This is the opposite for a west declination, and I don't have a formula for you because I've never worked or lived over there and had any reason to care. But the formula is the opposite. One big thing for the new guys to remember, and this is stuff that most people screw up, is that grid equals map and magnetic equals your compass. So if you start labeling stuff M, and then people are like, oh, the map, and they're going to get everything backwards. I like to label things with just the letters when I'm doing the math, but you have to remember what each thing means. So it might be worth writing down. So let's put this into some basic practice here. If we're working in a place with an east declination with a grid magnetic angle of 14 degrees, and we've got 37 degrees in our grid, and we're trying to get to a magnetic, you're going to subtract your 14, and it's going to give us a 23 degrees magnetic, or on our compass. If our magnetic, our compass, gave us a grid of 326, we add our 14 degree grid magnetic angle, and that's going to give us a 340 degree grid angle. Now if we were doing a west declination with a GM angle of 8, we'd have a grid of, in this example, 258. We're going to add our 8 degree grid magnetic, and we're going to get to a 266 magnetic angle. Or if we're starting with a magnetic angle of 176, we're going to take away 8 degrees to convert for our grid magnetic angle here, and we're going to arrive at a 168 degree grid angle here. Those are just quick examples. Now, if you're going to be going from 0 or 360, if you're going over the top, I don't know if this is going to show real well here. The tops, 0 and 360 degrees on our circle are the same thing. So if you're going past, you're going to either, once you hit 360, if you're going up, you're going to start over at 0. Or if you're going down and you hit 0, then you're taken away from your 360 degrees. Some examples, it's like, let's say we've got an east declination of 13 degrees. We've got a grid, an 8 degree heading. We're going to take away our 13 degree for our grid magnetic angle, and that's going to get us to 355. So if you take, you're at 8 and you go down 8 to get to 0, it means you've got 5 degrees left of this grid magnetic angle. 0 and 360 are the same, so 5, because that's what's left, less than 360 is 355. Going in the other direction, you've got a magnetic of 352. It's going to take 8 degrees to get to your 360. So we got 5 degrees left of our grid magnetic angle, and that's going to give us our 5 degree grid. It works the same way for a west declination, as you can see in the example there. So it's just remembering that that's where the math is at. If you're doing this in the table here in the house, it's real easy. You can do most of this math in your head if you're good at math. When you start getting tired, sweaty, wet, hot, cold, just doing this stuff in the field, it's worth putting everything on paper, because this is where your errors happen in your math. All right, thanks for joining us today. I hope that you learned something. This seems like boring, stupid math, but this is the little nuance that's going to really start to come together here. In a future video, we're going to be showing you how to get your angles both on a compass and on the map, and then how to do all the conversions and stuff that way. And then you'll actually be able to see how this comes together here in the future. But thanks for joining us. God bless.